Today we're going to cover Chapter 10, Days 6 and 7. We're going to combine them into one, where we're talking about vectors in the plane, but today we're going to talk about an algebraic approach. Okay. For any two coordinates of a vector, we have x1, y1, x2, y2 for points P and Q. The component form of this vector can be found using this right here. Do x2 minus x1, y2 minus y1. That is the component form of your vector. For vector addition, if we're adding two vectors together, we saw yesterday the geometric form, right, head to tail. Well, if we're doing vector addition with these two vectors, where, again, the horizontal component u1 and v1 and the vertical component u2, v2, we can apply that by adding the horizontal components together, adding the vertical components together, and getting the resultant vector. We can do the same thing with subtraction, scalar multiplication. If you're trying to multiply or scale a vector, you can multiply each individual component, the horizontal and vertical, to get the resultant. And then unit vectors, obviously a unit vector has one unit. So if you have a unit vector where the horizontal component is 1 and the vertical component is 0, we can use the letter I to represent that. And then the unit vector for a vertical component of 1 and a horizontal component of 0 can be written as j. So x comma y as a unit vector can be written as xi plus yj. So these are little pieces of information we're going to be using today. Make sure you have them down and make sure they're available to you. If you take a look at number 1, we're just trying to sketch and compute the length of 4 comma 3. So here's 4 comma 3. If we start at the origin and we work to that point, there's our vector that we're talking about. And again, we can find that length right here by doing the Pythagorean theorem or our magnitude that we learned yesterday. So we have 4 squared plus 3 squared, square root of 25. The length of this vector is 5. If we take a look at number 2, it says find the component form of the vector PQ. Well, now we're going to do an algebraic approach. So we're going to find the length by doing x2. Sorry, here we go. x2 minus x1, comma y2 minus y1. Now be careful. We have a double negative here. So we're going to double negative there, plus positive. So the vector that we're talking about is 0, comma negative 4. And we want to find the component form of that. Sorry, we're finding the component form. Thought we were going to find the magnitude. That's all we're finding right there. Component form of this vector. Number 3, we're going to do some vector addition and scalar multiplication. So again, you're just applying A, B, and C, those vectors in that key right there. So we're going to do 2 times A. We're finding the magnitude of all of this, by the way, at the end. So let's do 2 times 2 comma 3. That's our vector A. Plus, and then in parentheses, just like we treat our normal expressions, we want to do inside the parentheses first. So we have vector B, which is 5 comma 4, plus vector C, which is 6 comma negative 1. So again, just like we did with any expression, we're going to do inside the parentheses first. So you end up with 6 plus 5, you're going to get 11. And then, so those are horizontal components, and then the vertical components we add together as well. So the inside of that parentheses is just going to be 11 comma 3. And then because this wasn't really affected by that, we can go ahead and do our scalar multiplication as well. It's kind of like distributing. You end up with a vector of 4 comma 6. Now we're trying to add these two vectors. So again, the magnitude of 15 comma 9. Now we can do, since we're finding the magnitude of this one vector, we can apply the formula 15 squared plus 9 squared. You end up with the square root of 306. Let's reduce our radical to square root of 9 square root of 34. You end up with 3 root 34. So just going piece by piece, doing your vector addition and scalar multiplication. We did vector additions three separate times there. Take a look at 4a. It says express 3 comma 8 in terms of unit vectors. Well, we just saw at the very top, remember 3i, that's your horizontal component, plus 8j, that's your vertical component. Really straightforward. Go in reverse. Here's our horizontal component. We're going to component form this time. So 5 is our horizontal component. -4 is our vertical component. Hey, look at that. We got component form. Nice. Taking a look at number 5. We got to do a little bit of thinking here. So we're trying to find the unit vector in the same direction as this vector right here. So if we drew this vector on a graph geometrically like we saw the other day, we would say that the horizontal component is 6. So 1, 2, 3, 4, 5, 6. The vertical component is -3. So this vector looks just like this, right? Where we're going, if we make this right triangle, we're going 6 over and 3 down in this direction, okay? So obviously that magnitude in the direction of our vector is larger than 1. Unit vector means that it has a magnitude of 1, right? So what we're trying to do, and we could find this if we really wanted to. I can go ahead and do that. What's that? Square root of 36 plus 9, so that's square root of 45, right? That's the length of the actual vector. We're trying to find the unit vector that's going in the same direction. So we're trying to find this vector that has a length or a magnitude of 1, okay? So let's go ahead and talk about this. I already found it actually, but let's find the magnitude of the vector that we're actually looking at. So I just said square root of 45. This is going to be 3 root 5. In order to find the unit vector in this direction, what we want to do is we want to multiply our initial vector, multiply by the reciprocal. So we're going to multiply this, or you can divide it by the actual magnitude, but we're going to scale. Like we said, we're scaling this vector down so that it has a magnitude of 1. So by doing this, 6 over 3 root 5, comma, -3 over 3 root 5, you end up reducing it. We get, what is that, 2 root 5 over 5, negative root 5 over 5. So now this right here is our vector, as our unit vector, the horizontal and the vertical components. So this right here, if I made this right triangle, this would be 2 root 5 over 5 as the horizontal component, negative root 5 over 5. And that gives us a unit of 1. And again, all we did was we took the actual vector that we had, we found the magnitude of it, and then we multiplied that vector by the reciprocal of that magnitude, and it scaled it down, right? So if you're trying to turn a vector or find a unit vector in the same direction, what you do is find the magnitude and then multiply or divide by the magnitude, or you can multiply by the reciprocal. Number 6, it says if theta is pi over 6, we want to find the unit vector. Well, yesterday, if you recall, we said we could find the horizontal component by doing the absolute value. Not the absolute value, by taking the magnitude and multiplying it by the cosine of theta, and then the vertical component by taking the magnitude of your vector and multiplying it by the sine of theta, right? This is how you find the horizontal component. This is how you find the vertical component. You take the magnitude of the vector, multiply it by cosine of the angle you're talking about, and then magnitude, multiply it by the sine of the angle. Well, if we're talking about a unit vector, we just said it has a magnitude of 1. So all you have to do here is say 1 times cosine of pi over 6, 1 times sine of pi over 6. And then at this point, we are just fantastic with our unit circle. And we know that cosine of pi over 6 is root 3 over 2. Sine of pi over 6 is 1/2. So there is the component form of a unit vector in the direction of pi over 6 with an angle of pi over 6. On the next page, here's a couple other things that we want to make sure we're aware of. The dot product. This is an important concept. You end up with a scalar value, meaning you don't get a number, or you don't get a vector. You get an actual number. So when you see two vectors, u and v, with a dot between them, that is not multiplication. Okay? You need to know this because sometimes students, just like when we did addition, they would add the two x's, the two horizontal components, and then they would add the two vertical components. For multiplication, you don't just multiply the horizontal and multiply the vertical components. It's an actual thing. This is a dot product. So when you get the dot product of two vectors, you have to actually apply this formula right here. Then another part we're going to be using later is if you're finding the angle between any two vectors, this is the formula you're going to use. We're going to do the dot product up top and then the two magnitudes below. So we'll go through a couple problems here in a minute, but just to point that out at the top where we're getting these from. Number 7, it says find the direction, the angle, right, direction of vector AB with respect to the positive x-axis in degrees, given that A is 3,5 and B is negative 3,2. Well, the first thing we want to do is, because we're talking about in regards to the positive x-axis, let's go ahead and mark the angle that we're going from. Well, it says vector AB with respect to the positive x-axis, so let's just draw the vector with our starting point at the origin, because then wherever the vector goes, we can find that angle between our terminal side and that positive x-axis. So in order to do that, because these points, neither of them are at the origin, we want to find the component form of this vector. So vector AB, remember we can find by doing x2 minus x1, y2 minus y1. If we do that, we get vector AB is negative 6, comma negative 3. And again, this is our horizontal component. This is our vertical component. So from the origin, we want to go to negative 6, negative 3. So here is our vector AB. Knowing that, we can go ahead and make this right triangle. Again, horizontal is negative 6, vertical is negative 3. We can find this angle by doing the tangent of theta equal to negative 3 over 6, negative 3 over negative 6. Take the tangent inverse of negative 3 over negative 6 is 1/2. So the tan inverse of that is going to be 26.57. So this is our reference angle, but like we said in their initial directions, we're finding the direction or the angle with respect to the positive x-axis. So from here, you guys should be used to this. This is just how we started our unit circle, right? What is the full measure here? Well, if this is 26.5 roughly, and this is 180, we can just add 180 to that to get the full angle. So the full angle is going to be 206.57 degrees from the positive x-axis. Number 8, we got to do a little vector addition here. So the first thing we want to do, again, to make these easier to add rather than finding the coordinates and stuff, let's find the component form of AB. The component form of AB, you take x2 minus x1, comma, y2 minus y1. So the component form of this would be positive 4, comma 1. For CB vector, we would do 0 minus 2, and then was that 2 minus negative 3? So our component form for number 8 would be negative 2, comma, positive 5. Be careful about those double negatives, okay? So if these are the directions we're going, again, when we go to add these, let's fill it out in this equation now, or this, what we're trying to find. We have vector AB, 4, comma 1, plus vector CB, negative 2, comma 5. Add those together, we end up with 2, comma 6. Now, if we're trying to find the magnitude of that, that's what these two things mean right here. That's the magnitude. We go x squared plus y squared, square root it, 4 plus 36 is square root of 40. You can break it down to 4 and 10. So you end up with 2 root 10. So that's the magnitude of vector AB plus vector CB. And if we did it geometrically like we did yesterday, where it's head to tail, you would get the same thing. The last problem we're going to take a look at, two more problems. Number 9, we're going to go through, again, a little bit of algebraic process. So if we have vector u, let's just fill in what we know right now. We have -4, 5. And again, we're doing the dot product, not multiplying, with u parentheses v plus w. So we have 3, 4 plus w is 2, -5. Just like our normal expressions, we got to do inside the parentheses first. So we're going to do our vector addition first. So we have 5, -1. And then the other one is still -4, 5. Now, when we do the dot product, we haven't done one of these before yet. So again, up at the top, let's refer to the process. If we have vector u and vector v being dot product, we do u1 times v1, the horizontal components. Those we actually multiply. Then we add that with the vertical components that are being multiplied. So if we walk through that same process with these actual numbers, I multiply the x's, I multiply the y's, but then we're adding the results. So we get -20 plus -5. So the final result here is not, again, a vector, but rather a scalar. You end up with an actual number. The last problem we're going to do here says if theta is the angle between vector A and vector B, we want to find angle theta. Well, again, let's go back to our formulas up top. Angle between two vectors, right here, let's use this formula. Cosine of theta equals A dot B over magnitude of A times the magnitude of B. So again, if we did the dot product for those two right here, that would be A vector horizontal component of A, which is 5, times the horizontal component of B, which is 3, plus the vertical component of A times the vertical component of B. So the numerator is just going to be -15 plus -42. You end up with a numerator for the cosine of theta equal to -57. So there's our numerator. Now on the side, let's find the magnitudes of these two vectors. So for vector A, the magnitude would be 5 squared plus 6 squared, all in the square root. You end up with the square root of 61. For the magnitude of vector B, square root of, be careful with the parentheses, -3 squared plus -7 squared, you end up with the square root of 58. 49 plus 9, square root of 58, square root of 58. So the last thing we want to do here, because again, we're finding angle theta, is we got to take the cosine inverse of both sides to cancel out the cosine. So angle theta equals the cosine inverse of -57 over square root 61 times the square root of 58. You don't necessarily have to multiply those two together. You can just leave it as it's written as long as you type it in properly. So if we go ahead and type this in, and again, be careful if we're getting our answer in degrees, and it doesn't specify here, but make sure that our degrees is the mode that we're talking about if we're looking for degrees. So I would do second cosine, and then alpha y equals enter. That gives us the fraction, -57 over square root 61 times square root 58. Double check, make sure it all looks good, and we end up with an angle of 163.4 degrees.